Ladies and gentlemen, please welcome back Bruce Davie and our presenters.
All right, so folks can start lining up at the microphones if you've got questions. And first of all, I've got to say to the panelists, what an amazingly coherent set of talks. So first of all, how do you feel about BPF?
BPF is the future.
That was actually a joke question. Thanks.
I wish we'd never done it.
I guess while we're waiting for people to get warmed up there, and also one of my favorite tweets yesterday was somebody going kind of ballistic about the idea of somebody actually used the microphone to ask a question and how awesome that was. So just a little bit of encouragement to get to the mic if you want to ask a question. One thing I was wondering about, especially during the first couple of talks, was, as we talk about the rise of software networking, I think for most of us we think x86. And so I was wondering, do you think there is a role for other kinds of programmable hardware? And particularly, I think, as we think about some of the stuff that was at the end of Franz's talk, where you start thinking about your functions maybe moving around between servers and switches. Do you think there's a role here where some of that code that's going to run and do all these cool things might be on things other than x86?
Absolutely. So I think, in particular, if you look at BPF as one example, it was very x86 dominated in the beginning, and we now see the community providing JIT compilers, the compiler that turns the generic BPF bytecode into the CPU native instructions. We see JIT compilers coming up for ARM, Spark, and so on. So I think there is demand for taking software-defined networking, software networking onto non-x86.
And we see P4 having some role in that, perhaps?
Absolutely, I think so. I think Brandon actually demoed a P4 to BPF compiler at BPF workshop.
Yeah, there are a couple different implementations of P4 and other languages that as you build up your SDK, you have different pipelines that as long as the abstraction layer at each stage is defined, then you can keep pushing that down to different hardwares. You can swap out the hardwares as they come along if it's a performance or a scalability concern. And the language definition for the network engineers is important for their quality of life in terms of developing new applications. So the choice of language is definitely important.
Yeah. So I think just to add on to that, so I think it will depend on the audience that you look at in terms of who's going to write these programs. If you're looking at a Linux kernel developer background, he will always choose to write C code, BPF, close to BPF. If you're looking at a traditional software engineer, traditional network engineer, closest to the networking world, he will fall in love with P4 before he will fall in love with BPF bytecode.
Because we've got our first person up at the microphone, so do you want to just go ahead and ask your question?
Yeah, I have two questions.
So you only get one. No. Well, actually, just do them sequentially. So give us your first question.
Okay. So most of the enterprises use Red Hat Linux, 7.2, which has a kernel version of 3.10. Can we use BPF in that?
So the short answer is BPF has been around for a long while, but it has been evolving. So it will depend on what functionality of BPF you require. If we take Stellium as a specific example, we require a kernel 4.8 to function, which means that it will not work with URL 6 kernel, for example. Although there is a possibility of running a Linux kernel module to provide the runtime to all the kernels. That will be up to you whether you're willing to run.
It was initially developed as a kernel module and works but those implementations haven't been carried forward because you always want to upstream. And so if someone backports to RHEL, that's up to them. And there have been some attempts, but I don't think that that's necessarily in the cards.
I think Red Hat is a self-driven organization like many others. I've spent a long time at Red Hat, so I notice when customers demand BPF, Red Hat will provide a BPF runtime. I think for me the answer is as simple as this.
I guess the other question is around security. Our cyber folks would have a problem injecting code into the kernel. Should we be concerned? These compiling tool sets injecting code?
Yeah, so this was a very a big concern during the design of how to extend BPF, and something that we've gone through a lot of discussions about how to make that to secure. It has it has a verifier pipeline for uploading code into the kernel, and has to have a stringent set of checks. The verifier itself is something we've done and taken through different language fuzzers to look for bugs in the verifier. and that's a continuous area of research. And I mean, the design of the system itself is such that it should be, it should be fast, and it should also be predictable, which means no unexpected instructions in the program, and the kernel enforces that.
Yeah, actually, I just wanted to ask a follow-up on that, because that was something that intrigued me as well during your presentation, was the idea that you're asserting that, at least, that you can make sure that the code is safe to run in the kernel. Mm-hmm. And I was wondering, like, how much is that kind of a mathematically provable safety versus we haven't found any problems yet kind of safety?
So the verifier that's in there is C code. So that has, if you assume something about the baseline, but the analysis that it does itself is it treats it as a graph. It treats it as a computer science ASD built-in concepts that we have theory around, and does an analysis on that to prove those things with only caveats about bugs, not about the theory behind it.
Yeah.
Well, I think given that BPF will be the dominant technology for lots of kernel subsystems, there will be a high demand for a bug-free verifier, which means the community will put all eyes onto the verifier, and this has in particular been a major focus in improving the verifier and the correctness of the verifier. Yeah. And it's open source, the code is out there, you can look at the code, you can verify the code. So I think this will be a stable, highly trusted piece of software that was found in OS kernel.
And it is in fact, there is a mathematical rigor behind it, as well as the as we know, open source makes sure there's never any bugs in anything.
Absolutely.
Okay, we've got some more folks lining up at the mic. Let's go there.
Yeah, thank you. Firstly, great presentation by all of you. Fantastic work. There are a lot of moving parts to this. I just wanted to hear your thoughts on packaging and how it can be consumed easily. I mean, there is, I think, Calico, there's BPF, there's XPDR, and then there is a sidecar. I mean, any thoughts on how this is consumed even from an enterprise perspective? I mean, from a packaging standpoint.
From a packaging?
Yeah, and putting it all together and easily deployable and consumable.
So talking about taking the networking specific elements, so networking plugins, I would say, will be packaged depending on the orchestration system you go with. If you're taking Kubernetes and Mesos, it will come as a CNI plugin. So Calico, like Cilium, they all package themselves as a CNI plugin. If you're running on Docker Swarm, it would be a lib network plugin. So all of these orchestration systems have a pluggable system where you can basically, you can take one out and take the other one in. And in particular around networking and network security, there's open standards, which means as you write your network security policies, they will be compatible between the plug, or they should be compatible between the plugins.
Yeah, and then from an orchestrator perspective, like Kubernetes itself and Mesos, these are all systems that you're going to stand up, right? You orchestrate and manage the install of Kubernetes and Mesos. But once those are up, you have library systems. Kubernetes has something called Helm, and you can define Helm charts. In a Helm, you can actually go ahead and deploy Istio, Istio is just nothing but a bunch of containers running anyway. And the same with Mesos, it has something called the Universe. Universe, and this is specifically a feature towards DCOS. The Universe has packages built out with that functionality. It's actually pretty cool, right? It's not just for the functionality we talked about today. You can go stand up a Kafka server, you can go stand up Nginx, any of these pieces, just by going into that package manager of those orchestrators.
And maybe one more thought is that regardless of which technology we use, either for the application or for the infrastructure, they should be composable. And the things that an application requires shouldn't impose a restriction on the infrastructure and vice versa. So if you have an application that has a particular networking and connectivity requirement, the specification of that should go along and package with the application. And the requirements that the infrastructure has about providing security should go along with the infrastructure. And those need to be composable in whichever technology we choose and join them.
I'm going to insert myself in the stream here, because there was something that actually struck me a little bit through the course of the talks, was the sort of, I'd say there wasn't not a lot of love for the virtual machine across these three talks. So one of the things that I've heard asserted by people who may or may not work for VMware is that you need a separate protection domain to really get strong security. So the idea that like if you can compromise a single container on a Docker host, you've ultimately got the ability to start having lateral movement across the host. So if you really want strong security, you should put your Docker host in a VM and enforce security down in the hypervisor. Any thoughts or reaction to that?
Yeah, so it's interesting, the whole conversation between containers and hypervisor. If you think about it, we run our platform in the private data center or a private cloud, but we also run it very much in public cloud. And what is it running on in the public cloud? On a VM, right? That's what public cloud uses. So there's no real debate there regarding can you run a Docker container on a VM. For us in the data center, we've gone not with running them on VMs, even from a security perspective. We're leaning more towards the application providing the security, implementing that security on layer 7, right? There's some things that you need to do as far as following best practices when you launch containers, but we're on physical machines running CoreOS, and CoreOS runs the containers, and the containers run in the infrastructure. If there is any containers that is very specific towards needing security, say PCI compliance, we just stand up another cluster, right? So we just have another cluster stood up for PCI compliant containers, and that's where you're going to be. And there's more stricter rules about what those containers can do. So.
Yeah, I think it's not about not having a lot for VMs, but if you're consuming public cloud or the VM problem has been solved and you're consuming VMs automatically, I think if you're running in a private data center, you absolutely have the option to use hypervisor technology. There are multiple projects out there which use, for example, x86 hypervisor functionality and boot up a small Linux kernel for every container individually, which will provide you the hardware isolation.
Okay, thanks. Back to Mike.
First of all, great talks. Thanks for spending the time. So I'm very excited to see all this programmability, and I was a VMware before. I've seen it, the distribution of service, the programmability at the edge. Now I'm a Barefoot, and we, talk about programmability and the switching ASICs. So I wanted to pick your brain and ask you, so what do you see the good use case where you can extend this end to end? When we talk with customers, we see like telemetry being one of the use cases where P4 can be used to define this, across physical switches and, hypervisor eBPF in this case, also for bare metal services. And do you think telemetry is a good use case? Going back to the intent base we discussed yesterday, telemetry was like one of the weakest link because you cannot efficiently gather this telemetry data from the network. What do you think?
Absolutely, that's a use case, and with some of these technologies, you can take it even further in having instant feedback in your telemetry that you can feed into a quarantine action, or like doing immediate enforcement, because you have both the analysis engine down there at a very low level in the network, in the kernel functions, in the system calls, and then having a feedback into enforcement to change behavior as you see it happening.
Yeah, I think it's an opportunity to take monitoring from monitoring the network to monitoring your applications as they work on or as they run on the network. So seeing both the network packets and seeing the application behavior, system calls, I/O, all of this, and connect it together and report it as a whole, right? I think this is the opportunity that this provides.
Yeah, if you look at what Istio is calling out as one of its key features, it's actually telemetry data collection, right? And this is part of it.
Yeah.
Hey guys, I'm really interested in the future of programmability, and I was wondering if you could contrast P4 with BPF and perhaps other technologies in that space, and where you guys think it's going to end up in 10 years. Does BPF win? Does P4 win? Is P4 doing some subset and BPF is off doing something else? Does something else happen? What do you see?
I think of P4 as complementary and a layer above BPF. So I mean, when we did some of the prototyping of how to integrate those two, P4 is the description language of the functionality and how it works together, and BPF is one of the implementations. So it's BPF isn't a restriction about how the system behaves. It's just an instruction set in some terms. So you can use BPF to implement network functionality, and so they're complementary in that sense. And then if you have a programmable hardware or a programmable kernel, either one, you want an abstraction layer. BPF is a good version of that you can take your P4 program and have it run in lots of different places.
Yeah, I think there's a generic part of BPF that is, for example, applicable to offloading to hardware, and there's a part of BPF and a part of XDP which is Linux specific, as in particular if you go into helper functions, it's interacting with the Linux kernel, which means the assumption is made that this will run in a Linux environment where you can interact with the kernel. So it's definitely targeted for the Linux software world, whereas P4 is designed with, this should be a standard that works across software and hardware.
And I mean, there's nothing in BPF in the specification that says that it can only work on Linux. It's an instruction set with the ability to call functions. The most widely implemented set of those functions is in Linux, but it's programmable. It's an API.
Thanks, guys.
So the concept of infrastructure as code as delivered with all the tools that you gentlemen provide, which are great tools, is really good and powerful. But there seems to be this lack of attention on the underlying hardware, and we're still stuck in vendor-specific implementations when it comes to automating and managing the underlying hardware. Do you think there's a path forward where the techniques you're using to automate your programmable infrastructure can live in harmony with the underlying physical infrastructure, and they can all be in the same ecosystem? Is that something we can expect?
I think I'm really the wrong person to answer that question.
I'll pretend I'm a panelist now. Since I thought the end of Franz's talk started to address that question, because it sort of showed how switches could start to look a lot more like servers. And so there was, I think, almost the last slide of your presentation with that talk project. It was almost like the switches had code running on them, and you could deploy containers onto them. And so you could, because the switches were very, very different right there.
x86 PCs, and your x86 PCs are now network switches, so let's all play together.
Yeah, and so you could certainly imagine a world in which the same kind of rigor that we apply today to deploying application software with automated test and Jenkins and so on, all of that sort of methodology could be applied to the network. And this, I think, was mentioned yesterday as well, the idea that we do networking in a very, very sort of 1980s way most of the time today, and we get unpredictable results. We could actually adopt 21st century software development methodologies and apply it to networking if we had the right tools. And I think Ratul's talk made that point in one way, and I think the sort of the talk example is another way you could see that playing out, where if your network gear starts to look more like your other types of application infrastructure, now you could start applying the same methodologies, and now your infrastructure is managed like code, and you get that sort of repeatability.
Yeah, so just to give an example there, right, and I didn't go too deep into it, but one of the projects we're working on right now is called it's a Greenfield project, and we actually called it, we're pretty imaginative here, we called it Greenfield, right? And so what this is to fully automate the stand-up of infrastructure, right? So you have like your tools like Terraform where you can define your infrastructure as code, but if you think about it, that really applies to the cloud, right? I can run a Terraform template in AWS, I can run it in Azure, and it's actually going to stand up the whole infrastructure. But if I run it in a data center, if I'm not running OpenStack, and I have all of these exceptions in the data center. And we didn't want to run OpenStack simply just to automate the stand-up of infrastructure. It has to be a simpler way of doing it or a cleaner way. And so we found an open source project. It's actually by EMC, the EMC code guys. It's called RackHD. And all it does is what you want to do is you just want to discover and you want to inventory what you get. Whether that be a switch or a server or whatever, you just want to have the thing boot, discover, and then say, here you go, here's your software, which is Linux, right?
Yeah, so that does kind of power and auto provisioning and stuff. The one, I actually looked at RackHD, that there seems to be a lack of code examples for a lot of the use cases, so I'd be interested if you have anything you've published on your use of that.
And we do. We've actually contributed back a little bit, and I'd love to talk to you about it after, too. Be happy to. So, but that's kind of where it's going, right? But from there, the automated process takes over. You have a base operating system, which is Linux, and from there, you can actually build out your role and get your containerized platform going. The main thing that we did is we saw we had a chicken egg problem. How do you start your whole infrastructure up when you have to have Greenfield? Because we said we're completely separated from the network. What we did was we actually used a switch to run a container of RackHD to discover the rest of the machines as they came up, right? So our switch suddenly started functioning more as a network switch it was one of the nodes that we actually relied on to run containers to do discovery and pixie booting of everything. Here you can see, and it's a very simple example, right? It's not like everything.
I think that would make an amazing blog post if you ever have time to work on it.
And I'd be happy to do that because the switch became the primary stand-up of everything. Like literally we started with a switch, the switch booted, right? You have to have a base OS on that switch, but the rest of the switches and it's funny because we actually use the Facebook wedge for that switch, which is also a very cool thing. But the rest of the switches which came up got their config from the master, right? They got their configuration from the master. Nobody touched the switch, nobody SSH'd into it, nobody did any config on them. And then from there, the machines would come up, the nodes, right? The nodes came up, they configured themselves from that master switch. They became just generic cattle. The orchestration platform landed on top, and we had an orchestration platform. Now you're running containers all over the place, right?
All right, so speaking of predictable execution time, we are down to minus 1 minute now, so can you ask your question extremely quickly?
I was hoping to tie up the last couple of questions. They all seem flirting around the same issue, which is, in my mind, there's a fundamental difference in the forwarding performance you get out of x86 versus kind of a dedicated packet processing ASIC. And like, I am blown away constantly by the speeds you get out of eBPF, and like, great, but that's still like several orders of magnitude what you get from like a top of rack switch. And so, call it a question, call it a comment. We can end the conversation here. We could segue to my talk that takes up this exactly after lunch. But
all right. Well, thank you for introducing your own talk, and I think we'll cut it off there. All right. Thanks, everybody.